This is review video 27. What is a potential energy graph? So if you've taken chemistry before, you've already seen a potential energy graph. They look like this, so they should look fairly familiar to you. But specifically what they are is a graph that shows energy changes over the course of a chemical reaction. So they'll show how much energy the reactants have to begin with. They'll show how much energy it takes to break the bonds during that reaction. They'll show how much energy is lost or gained over time, basically just any changes that occur over the course of that reaction. And there's a few different pieces of a potential energy graph that you need to be aware of. The first is the energy of reactants, or E sub R. And the second is the energy of products, or E sub P. So if we go all the way down here to our potential energy graph, I'm going to label those for you real quick. This first flattened section here is always going to be E sub R, or the energy of the reactants. This is how much energy the reactants have to begin with. All the way at the end of the graph over here, this second flattened spot is always going to be E sub P, or the energy of products. So that's where our reaction ends. That's how much energy our products have overall. Going back up, the next one you want to be aware of is E sub A, or the energy of activation. And that is how much energy input is required to start the reaction, or how much energy is required to break all of the reactant bonds. So if we look at this sample equation here that I've given you, which is the synthesis of water, the energy of activation is going to be how much energy it takes to break this and this and this. And that is represented by the height of the hill on the graph. So let's go down and let's label that on this graph right here. This distance from where energy of reactants is to the top of the hill, that is E sub A. That's the energy of activation. This is not E sub A, because the top of the hill is actually called something else. It's called the activated complex. And the activated complex is just the highest point in energy in any reaction. But again, E sub A, or the amount of energy required to break any reactant bonds, is always this entire distance from E sub R to the activated complex point C. All right? Last thing you need to be aware of in a potential energy graph is delta H, or the change in enthalpy of a reaction. And what that is the net loss or gain of enthalpy over the course of the reaction. And enthalpy is not a term I want you to get tripped up on right now. We'll talk a lot about enthalpy during the thermodynamics unit. But for right now, all you really need to know about it is that it is similar to energy. It is not the same thing, but for all intents and purposes right now, this term is going to be similar to energy. So you can think of it as the energy lost or gained over the course of the reaction. If you see a delta H that is positive, that means that the reaction has absorbed or gained energy over time, and we call that an endothermic reaction. In an endothermic reaction, you'll see a potential energy graph that looks like this. Specifically, your energy of reactants is lower than your energy of your products, indicating that overall those chemical species have absorbed energy from the outside. Now, another thing that's special about endothermic reactions is that if you hold one in your hands, it feels cold. Specifically, it feels cold because you are the surroundings of the reaction. So if you're holding it and that reaction is absorbing energy, it's absorbing it from you. And so you will feel cold if you hold one of those reactions in your hand. However, if you see the opposite, if you see a delta H that is negative, that reaction has lost energy or released it to the surroundings, and we call that an exothermic reaction. Their potential energy graphs look a little different, so you'll see something that looks like this, where our E sub R is always higher than our E sub P, indicating that we have lost energy to the surroundings over time. Those reactions, if you hold one in your hand, will feel hot or warm to you. Fire is an excellent example of an exothermic reaction because it's releasing a ton of energy to the surroundings, and if you were to hold it, you would get burned. Now, on this graph down here, the delta H value is always, always, always going to be the distance between E sub R and E sub P, because that is the net enthalpy loss or gain over the course of the reaction. Again, it doesn't include any of this, absolutely not. It's just the distance between E sub R and E sub P. All right? Down here, here's a couple of examples of an exothermic versus an endothermic reaction. So on the left, we see an exothermic. Again, those are going to be the ones that release energy to their surroundings. On the right, you see an example of an endothermic reaction that is going to absorb energy from the surroundings. So we see a net loss of energy in our exothermic, and we see a net gain of energy in our endothermic. If you have any questions, comments, or concerns, please talk to me in class.